Let's make that visible with a live meter. As I rotate the direction arrow all the way around, watch a bar that tracks the variance of the shadows. The bar rises and falls smoothly. It peaks when the arrow lines up with the cloud's longest stretch, and it bottoms out 90 degrees away. The direction where that meter hits its maximum has a name, the first principal component. It is by definition the single direction along which the data varies the most. If you were forced to describe this whole two-dimensional cloud using just one number per point, projecting onto this line would preserve the most information you possibly could. Now, what about the direction of least spread? In 2 dimensions there's a natural candidate, the direction perpendicular to the first one. It turns out this perpendicular direction is the second principal component, and it captures whatever variance is left over after the first one has taken its share. Together these 2 arrows form a new pair of axes, custom fit to this particular cloud. They're not horizontal and vertical, they're tilted to match the data itself. Think of it as the cloud choosing its own natural coordinate system, one aligned with how it actually spreads rather than with the axes we happen to measure in. Let's actually rotate into that frame. I'll spin the whole picture so the first principal component becomes horizontal and the second becomes vertical. Watch what happens to the cloud as it turns. It settles into an orientation where its long stretch runs left to right and its short stretch runs up and down. Something subtle just happened. In these new coordinates, the cloud no longer leans. Knowing a point's position along the new horizontal tells you nothing about its position along the new vertical. We say the 2 new coordinates are uncorrelated. PCA has untangled the diagonal relationship that was there in the original height and weight picture. So far this has all been geometry, arrows and shadows. But to compute these directions we need a bridge to algebra, and that bridge is one of the most important objects in all of data science, the covariance matrix. Let's build it up slowly, piece by piece. The covariance matrix summarizes how the coordinates of the data vary and covary. In 2 dimensions it's a small 2x2 grid of 4 numbers. The top left entry is the variance of the first coordinate alone. The bottom right is the variance of the second coordinate alone. These 2 live on the diagonal. The 2 off-diagonal entries hold the covariance, a measure of whether the coordinates rise and fall together. If large X tends to come with large Y, this number is positive. If they move oppositely, it's negative. And if knowing one tells you nothing about the other, it's 0. For our tilted cloud, this off-diagonal number is clearly positive. There's a lovely way to see this matrix. It doesn't just store 4 numbers, it defines an ellipse, the shape that best hugs the cloud. The matrix stretches a plane circle into exactly the tilted oval our data traces out. So the covariance matrix and the shape of the cloud are really the same information wearing 2 different outfits. Now we ask the algebraic version of our earlier question. This matrix, thought of as a transformation, pushes and pulls vectors around. Most vectors get knocked off their original line when the matrix acts on them. They come out pointing somewhere new, but a special few keep pointing exactly the same way, only getting longer or shorter. Those special direction-preserving vectors are the eigenvectors of the covariance matrix. And here is the punchline of the entire subject. The eigenvectors of the covariance matrix are exactly the principal components we found by rotating that arrow. The geometry and the algebra meet. The directions of maximum and minimum spread are the eigenvectors. Each eigenvector comes paired with a number called its eigenvalue, the factor by which that special vector gets stretched. And these eigenvalues aren't arbitrary either. Each eigenvalue is precisely the variance of the data along its eigenvector. The bigger the eigenvalue, the more the data spreads in that direction. So now we can rank our directions by importance in a completely principled way. Just sort the eigenvalues from largest to smallest. The eigenvector with the largest eigenvalue is the first principal component, capturing the most variance. The next largest is the second, and so on. Importance is literally eigenvalue size. Let's put a number on it. Suppose the first eigenvalue is much larger than the second. Say it accounts for 90% of the total variance. That means 90% of everything interesting about this cloud lives along a single direction. The other direction, the thin one, carries only the remaining 10%. This is what makes PCA a tool for compression. If almost all the variance sits in the first component, then we can afford to throw the second one away. We keep only each point's coordinate along the top eigenvector, and describe our two-dimensional data with just one number per point. Let's watch that happen. Here goes the dimensionality reduction. Every point slides down its perpendicular onto the first principal component line, collapsing the two-dimensional cloud onto a single line. What was a plane full of dots is now a string of dots along one axis. We've reduced the dimension from 2 to 1. Of course, we lost something. Each point's little offset in the second direction is now gone. But because the second component held so little variance, those offsets were tiny to begin with. We compressed the data, and we can measure exactly how much we gave up. That measurement is the reconstruction error. So we project that 50-dimensional data down onto its top two principal components and plot it on a flat screen. Structure that was invisible, clusters, trends, outliers, suddenly appears. This is why PCA is everywhere. It finds the few directions that carry the story and lets you throw the rest away with confidence. Let's tie the whole journey into one loop. We started with a lopsided cloud and asked which direction it spreads the most. That question in geometry is a rotating arrow chasing maximum shadow spread. In algebra, it's the eigenvectors and eigenvalues of the covariance matrix. Same answer, two languages. The covariance matrix was the pivot. It converted the vague notion of spread into a concrete transformation whose special directions we could solve for exactly. The eigenvectors gave us the axes, the eigenvalues told us how much each one mattered, and sorting them handed us a ranked recipe for compression. And reconstruction error closed the loop, proving that keeping the biggest components isn't a hopeful guess but the mathematically optimal thing to do. Every eigenvalue you drop is exactly the error you accept, no more, no less. That clean accounting is what makes PCA trustworthy. So the next time you meet a tangled, high-dimensional dataset, remember the little tilted cloud we started with. Somewhere inside all that noise are a few directions doing most of the work. PCA is simply the art of turning to face them. Find the spread, and you find the structure. If this made it click, subscribe for more visual math.